I am going to introduce Gaussian random variable in this lecture. It is called Gaussian or normal distribution, and it is the most important distribution in all of probability theory. It plays a very vital role, that is very central role in probability theory. It shows up all over the place, and everywhere we can see this Gaussian random variable. It is also called a normal random variable. Okay, and in this lecture series, later on we will see why it shows up and why it is so important. Okay, now let us see the mathematics behind this and how do we interpret this. Okay, so what's the math involved here? All those things we'll see in this lecture. So the standard normal random variable, it is written by f sub x of x equal to f sub x of x equal to 1 over root of 2 pi e to the minus x squared over 2. So this is a density function. Now let us interpret this formula. Take the exponential. Okay, so we start with the exponential part, that is x squared over 2. Okay, let us take this function x squared over 2. Now if you want to plot this x squared over 2, it is a parabola, and the parabola shape will be like this. When x equal to 0, you will get a 0 point. When x equal to 1, 2, 3, then it keep on increases, and here also it keep on goes like this. It's a parabola. So now then what do we do? Take the this x squared by 2 and negative of this x squared by 2 and raise it to the e. Therefore we take negative exponential of this, so e power minus x squared over 2. Okay, so now when x equal to 0, then what happens in this curve? When x equal to 0, this implies 1. When x goes to infinity, then also it goes to 0. When x goes to minus infinity, then also it goes to 0. Therefore e power minus x squared curve will looks like this. When x equal to 0, 1, then it slowly decreases and goes to 0, 1. And from this side also slowly it goes to 1. Okay, therefore when x squared by 2 increases, the negative exponential of that falls off. It is falls off, and falling also pretty fast. So in this it goes up. Okay, the formula for the density goes down, but here it goes down because exponentials are pretty strong in how quickly they fall off. This means that the tails of this distribution actually goes down pretty fast. So this part is called a tail of the distribution. It goes pretty fast. So that explains the shape of the normal PDF. Now one can ask, why this 1 over square root 2 pi, this 1 over square root 2 pi, what does this where does this come from? Well, the integral has to be equal to 1, because in the previous lectures we have seen that if you take any density function and integrate from minus infinity to plus infinity, fx of x times dx should be 1 or must be 1. Therefore in order to make this area should be equal to 1, this 1 by 1 over root 2, root of 1 over root 2 pi has come. Okay, so you have to go to and do your calculus exercise and find the integral of this. So minus infinity plus infinity fx of x times dx, which is integral of minus infinity plus infinity e power minus x squared over 2 times dx. And now you just figure out what constant do I need to put in front here in this point. In order to make this integral should be equal to 1. So how do you evaluate the integral? Either you go to Mathematica or Wolfram's alpha to solve this equation, solve this integral. You can take Mathematica or Wolfram's alpha and you can solve it. It is a very beautiful calculus exercise that you may have seen at some point in your beta course. Okay, you throw in another exponential of this kind in this, another exponential. Okay, and you bring in polar coordinates and somehow the answer comes beautifully out there. So but in any case, this is a constant, this 1 over root 2 pi is a constant that you need to make it integrate to 1 and to be a legitimate density, otherwise it cannot be a legitimate density. Therefore your density function is fx of x equal to 1 over square root 2 pi e to the minus x squared by 2. Okay, and for the normal standard normal, what is we need to find out the mean and variance. Okay, how do you find the mean in this? By looking at the curve, the center point, the center of gravity. Mean is actually the center of gravity. The center of gravity is 0, right? Therefore the mean is, straight away you can write mean equal to 0. Okay, by symmetry you can write. So this is a shortcut in this. But what is the variance? Variance, how do you find the variance? Well, here there is no shortcut to find the variance. Okay, you have to do another calculus exercise and you find that the variance is equal to 1. If you do that exercise, the calculus exercise, then it will be end up with 1. Okay, so this is a normal that is centered around 0, this density function. And how about the other types of normals that are centered at different places? See here, this normal is centered at 0. Suppose I may have the normal at some other center location, maybe some others, maybe 1 or another normal like this, center maybe 2. Okay, so how do you describe this? So we can do the same kind of thing. Instead of centering at 0, we can take some place where we want to center it. Let's say I want to center it at x equal to mu. Therefore you write down the quadratic equation, x minus mu the whole square. So if you draw the x minus mu the whole square, then your quadratic will be like this parabola, but the parabola touches the 0 point at touches the 0 line at x equal to mu, and again beyond x equal to mu it increases, and here also it increases. You take the negative of this, negative exponential of this x minus mu the whole square. Okay, and that gives us the normal density that is centered at mu. So e to the minus x minus mu the whole square. Therefore you'll get like this. So here this density is centered at x equal to mu. Now I wish to control the width of my density. How do you control the width of the density? See, this is the normal function with the sigma equal to 1. Now I want to control the width. That means either I want to draw the figure like this, very large variation, or very less variance like this, or I can draw like this, very small variations like this. So how do you control the width? How do we control the width? So that is the next question one can ask. So if my parabola is narrower, if my parabola looks like like this, what is going to happen to the density? It is going to fall off much faster. Why? How do I make my parabola narrower or wider? I do it by putting in a constant constant term down the x minus mu. So x minus mu the whole square, if I put some constant, and this constant is a fairly small number, fairly small, the whole thing will be big value. Okay, therefore it rises very sharply, and if you take negative exponential of this, then you have like this. Therefore the denominator part will control controls the width of the normal distribution. Okay, if you put a very large value, very small value, then this x minus mu the whole square will be very big, and in that case the parabola will be very sharper. And if you take negative exponential of that, then the curve looks like this, very sharper curve. Suppose if x minus mu the whole square divided by, if you put a large number, then what happens? This whole thing will be very small number. Very small means it increases very slowly like this. The parabola looks like this. Okay, very big parabola. And you take negative exponential, the negative exponential also look this, like this. You'll get very big, very wider normal distribution. Therefore, the denominator part controls the width of the normal distribution. Therefore, so in general what we do is we x minus mu the whole square divided by sigma square. This stretches or widens my parabola by a factor of sigma. So let me call this sigma stretches or widens the parabola. So based on the parabola, your density function also going to be changed. Let's say if sigma is very small, no, less than 1, very small. Therefore, this implies x minus mu the whole square is a big number, right? Big number. So my parabola goes up quickly, which means my normal falls off very fast. So the parabola goes like this, very quickly it goes up. If you take the negative exponential of this, my density function, it starts from 1, it goes very quickly. Very quickly. So it should be intuitive that the standard deviation is proportional to sigma. So my standard deviation is proportional to sigma. If you decrease the sigma, then it widens it stretches, and if you increase sigma, then it widens. Okay, so that's the amount by which you are scaling the picture. So indeed the standard deviation is sigma. But what about the variance? Variance is the sigma squared. So all that we have done here to create a general normal with a given mean and variance is take this picture normal, this one normal distribution with sigma equal to 1 and center 0. Okay, and then scale it by a factor of, this is x e power minus x square by 2. Scale it by a factor of sigma. This gives us a normal with a given mean and variance. Therefore, you scale it, shift to the mean point, shift to the mean point and scale it. Therefore, shifting the mean point is x minus mu the whole square from x square to x minus mu the whole square, and instead of 2 we put a sigma square. Okay. Therefore, your general density function of your normal random variable is 1 over square root 2 pi sigma square e to the minus x minus mu the whole square over 2 sigma square. Or either you can write 1 by sigma root of 2 pi e to the minus x minus mu the whole square over 2 sigma square. Now in this expression, if you substitute sigma equal to 1 and mu equal to 0, you'll get a normal density function. Therefore, in short form, this normal random variable is denoted by mu comma sigma. These are the two characterizing parameters of your normal random variable. Okay. So therefore I can write as n of mu comma sigma for standard normal where mu equal to 0 and sigma equal to 1. So in such a case we will write n of 0 comma 1. That's it. resistant and normal. Okay, so in the next lecture I'm going to talk about the properties of your normal random variables, like your linearity property, and once you take the linearity, how its shape changes, all those things, and later on we'll do some problems on this. Okay, so at this point I'll stop this lecture. Thank you.